Hello class. This video is an introduction to graphing rational functions, and it assumes that you already have an understanding of vertical and horizontal asymptotes, which we've discussed in class. The next slide lists all the steps needed to graph these functions. So I'd like you to pause the video there to copy the steps into your notes. I know this looks a little overwhelming, but I think you'll see as you start writing them down that we actually know how to do all of this already. We just need to compile our prior knowledge to put together these steps so that it's easier to graph these rational functions. On the next slide, I go through an example. Now that you have all of the steps written down, let's see how we apply them. So step 1 is to find the y-intercept. We've been doing that for years. We let x equal 0, and that gives a y-intercept at -3/4. So we now have one point that we can plot for this rational function. Step 2 tells us to factor the numerator and the denominator, which I've done here. The numerator was already factored. And if we have any common factors, those will be holes in the graph. I don't have any common factors in the numerator and the denominator. If, for example, this factor were x plus 3, then I would have a common factor and there would be a hole on the graph at x equals -3. I have an example with that next. So we factored this, and now the factors in the numerator will become the x-intercepts of the graph because I'm technically letting y equal 0. And if I let y equal 0, this fraction has to be 0, and that happens when the numerator is 0. So we have one x-intercept on this graph at x equals -3. Okay, step 4 has us find the vertical asymptotes, and for that we focus on the factors in the denominator. As we know, the denominator of a fraction cannot equal 0, or else the fraction is undefined. And so the two values that will make the denominator 0 will end up being our two vertical asymptotes. So we're going to have vertical asymptotes at x equals 2 and x equals -2. For the horizontal asymptote, remember we're looking at the highest powered terms in the numerator and the denominator. So the degree in the denominator is 2 and the degree in the numerator is only 1. And when that's the case, when we're left with an x in the denominator, we'll have a horizontal asymptote at y equals 0. We spent a lot of time discussing that in class. So now we have our vertical and horizontal asymptotes, which we should put on a graph. So on the next slide, with our 6th and final step, I will graph this. I've started my sketch by putting in the pieces that we found in the previous steps. So I have my y-intercept at -3/4, my x-intercept at -3, my two vertical asymptotes at x equals -2, which comes from this factor, and x equals 2, which comes from this factor, my horizontal asymptote, which is at y equals 0. And if you look back at your notes, you'll see that in step 5, I mentioned that a graph can, in fact, go through a horizontal asymptote. And that's going to happen here because I have my horizontal asymptote is at y equals 0, but I have an x-intercept at a -3, 0. So I know you've learned in the past that you can never go through a vertical asymptote, but it's not actually the case with horizontal asymptotes. Around the origin or at your x-intercepts, a graph actually can go through a horizontal asymptote because the horizontal asymptote is actually discussing what's happening as x goes off to infinity and as x goes off to -infinity. We are nowhere near -infinity when we're here. So the horizontal asymptote technically doesn't exist around, I'm putting in quotes, the origin, only for very small negative or very large negative numbers and very large positive numbers. Okay, time for our sign analysis. So step 6 says to perform a sign analysis, and it discusses each section of the graph. The sections of the graph are broken up by things that are happening on the x-axis. So the first section of our graph is occurring from -infinity up to -3. The graph is doing something here. Is the graph above the x-axis or is the graph up below the x-axis? We know it can't cross the x-axis until we get to -3 because this is our only x-intercept. This is the only place the graph will cross the x-axis. So to see if the graph is above or below, I just test a point over here. I could try -4, I could try -4 million. I go up to my function and I'm putting in -4. Well, -4 will put the numerator as being negative because we would get -1. So the numerator is negative. -4 plus 2 is a negative. -4 minus 2 is a negative. And a negative times a negative is a positive. So we end up with a negative over a positive, which is a negative number. So in this section of the graph will be negative, which means it's going to be below the x-axis. Since I have a 0 here, most likely it's going to cross, and in this next section between -3 and -2, it's going to be positive, but let's double check that. So if I let x equal -2.5, when I substitute that into the numerator, I get positive number, 0.5. -2.5 here gives me a negative, and -2.5 here gives me a negative. Negative times a negative is a positive. So I end up with a positive over a positive, which is, of course, a positive. So it is true that between -3 and -2, the graph will be positive. It also must approach this vertical asymptote. So if I wanted to start sketching now, I know that my graph is coming in from the left. It has to be approaching this asymptote, right? So it has to be really close to the x-axis here. Maybe it drops down a little bit, but then it has to go through my x-intercept at -3, and then the graph is positive, and it's got to get closer and closer and closer to this vertical asymptote. So I'm not exactly sure what's going on over here on the left, but I know that eventually the graph is going to hug the x-axis on the negative side of the x-axis. So that's the first piece of our graph, or two pieces technically. Okay, now if I look at the next section of my graph, it's in between these two vertical asymptotes, and I actually have already tested a point because I have my y-intercept in here. So the graph has to be negative along this entire portion of the graph because it can't cross the x-axis and be positive. There would have to be another x-intercept, and there is not. Which means that the graph is trapped below the x-axis between these two vertical asymptotes. I know it has to go through this point, and I know it's going to, as it goes towards -2, it's going to have to get sucked down into this asymptote. It can't get drawn in going up because, as we've already talked about, it would cross the x-axis. So it has to get drawn into this vertical asymptote here and over here. I'm going to draw it as if it's symmetric, but in fact it's not symmetric. But don't even worry about that. Okay, so I've drawn this as if it's slightly parabolic. Of course it's not, because parabolas don't have asymptotes. In fact, I did graph this beforehand, and it goes a little more up here like this. Again, that's very minor, and we're not going to worry about it. Okay, in our last section, I now check when x is greater than 2. So 3 seems like a great point to check. So when x is 3, I go up to my function, and I put in 3, definitely positive in the numerator, positive for this factor, positive for this factor, positive all over. So the graph must be positive in this entire section, which means it's up here. Don't forget, it's going to get drawn into this asymptote, and the only way it can do that is by going up, because if it went down, it would cross the x-axis, which it does not, and it would become negative, which it does not. It also needs to get drawn into this horizontal asymptote as x goes off to infinity. So this piece looks like this. Now, this is just a sketch, so maybe in fact, it looks like this, but those are basically the same for our purposes. So here we go. I've graphed our first rational function. I'm going to do 2 more examples, but I'm going to go a little faster. Here's our second example. Step 1 says to find the y-intercept by letting x equal 0. And so the y-intercept is at -1/3 when you reduce. The next step says to factor both the numerator and the denominator. And when I factor the numerator, I get x plus 2, the quantity times the quantity x plus 1. And in the denominator, I get x plus 2 times x minus 3. And I did this on purpose because you'll see that we have a common factor in the numerator and the denominator of x plus 2. If you look back at your notes, you'll know that that means there's going to be a whole when x plus 2 equals 0. So this example has a hole at x equals -2. So the graph is not defined at x equals -2. But to make it easier to graph, I'm now going to cancel out that common factor because I've made my note that x cannot equal -2. And so we'll now proceed with this simpler version of just y equals x plus 1 over x minus 3. And when I go to graph it, I'm going to have to remember to make sure I have an empty circle at x equals -2. The next step is to find the x-intercept, and I do that by setting the numerator equal to 0, because I'm really saying that y is 0. And so we have our x-intercept at x equals -1. The next step is to find the vertical asymptotes. So there's only one vertical asymptote because remember the factor at x plus 2, that's going to lead to a hole. So the vertical asymptote is at x equals 3. And for the horizontal asymptote, I can use my original function or my reduced function. Either way, I'm only keeping the highest powered terms in the numerator and the denominator. And when I reduce those down, I would end up with a horizontal asymptote at y equals 1 in this case, because x squared over x squared is 1. So now I'll take all of the pieces that I've gathered from my steps, and I'll plot those on my axes. Now I need to perform my sign analysis to see when is the graph above the x-axis, so when is the graph positive, and when is it below the x-axis, when is it negative. What's nice is that I can use this reduced function for my sign analysis. The different sections of my graph in this case are from -infinity up to -1, between -1 and 3, and after 3. So let's check if x is a large negative number, or at least something smaller than -2, because we know we have our hole at -2. So I could actually still figure out, though, the value of y when x is -2, because in fact I want to make sure I have an open circle there. So I'm going to check when x is -2. So I put that in here. I end up with -1 in the numerator, and -2 minus 3 is -5. -1 over -5 is positive 1/5. So in fact, I'm going to put that in now. I have an open circle at -2, 1/5. So that also told me that the graph is positive there. Okay, from this I actually have enough information to go from -infinity all the way up to my vertical asymptote at x equals 3. So we know that before -2, the graph is positive, and it has to be getting closer to my horizontal asymptote, which is at y equals 1. Now, if I continue on the other side of x equals -2, so if I go to the right of x equals -2, I know I have to get through my x-intercept, which is at -1. And I also know I have to get through my y-intercept, which is at -1/3. And after that, I know eventually this graph is going to go down. Of course, I didn't give myself enough room, and get much, much closer to my vertical asymptote, which is at x equals 3. So unfortunately, I don't have enough room to show that it's going to get super close to x equals 3. So that's the first branch of this rational function. I also need to test a point after x equals 3, and so for that, I'll check when x is 4. And a quick check shows us that we end up with a positive over positive, which is positive. So I know for all values where x is greater than 3, the graph has to be positive. I know it can't possibly become negative because that would mean it would cross over the x-axis, and if that were true, I'd have to have an x-intercept over here, and our only x-intercept was at x equals -1. So now if you think about it, the graph has to get closer and closer to this horizontal asymptote and closer to this vertical asymptote, but it has to be positive. So it can't be happening in here, because if it were to happen in here, it would cross into the negatives. So it has to be trapped up here in this little corner from my two asymptotes. So I now know that the graph goes like this. It's going to get closer and closer to the two asymptotes. So these are the two branches for this rational function. Okay, I'm going to show one more example that includes a slant asymptote. For this example, I recommend that you pause the video and try and complete the steps on your own, and then you can verify them with my information. Okay, so you can see that I've done the steps over here on the right. The y-intercept is -4. I've factored the numerator. The denominator didn't need to be factored. And I notice there are no holes. Here are my x-intercepts and my vertical asymptote. There is no horizontal asymptote because I'm left, the highest powered term is in the numerator, which means when I reduce these, I'm left with an x in the numerator, which means there is no horizontal asymptote. In fact, there's going to be a slant asymptote. As we discussed in class, this means I'm going to need to use either synthetic or long division to figure out the equation for my slant asymptote. I'm going to choose synthetic division. So here I've done the work for synthetic division. I've divided by the 0 that's at x equals -1, but in fact it's not a 0, as we can see, because I have a remainder of -3. So now actually I know that when x is -1, the y value is going to be -3 for my remainder theorem. So I've done the division. This was a quadratic, so now this is my linear function, so the coefficients are 1 and -1, and so the slant asymptote is going to be at y equals x minus 1. That's the slant asymptote. Okay, I'm going to put all of this on a graph and then do my sign analysis. Okay, now for the sign analysis. To save a little time, I'm going to tell you that to the left of -2, the graph is negative, and in between -2 and -1, the graph is positive. And so it will look something like this. It's going to get closer and closer and closer, I'm using yellow, sorry, to this diagonal slant asymptote here, and then it's going to get closer and closer and closer to our vertical asymptote here. On the other side of things, it looks kind of similar. I know I have to go through this y-intercept and this x-intercept, and so if I start down here, I get closer and closer to this vertical asymptote. I have to go through my intercepts, and then eventually I will get closer and closer and closer to this diagonal asymptote, or my slant asymptote. So this is the graph for this rational function. I hope this video was helpful, and I'll see you in class.